Okay, hello everyone and welcome. Thank you for joining us this afternoon. For those of you who don't know me, my name's Helen Spiers and I've been organising this webinar series as part of the efforts of CCP-volumeEM. We're also joined today by Martin Jones, who is co-host of this session and PI of CCP-volumeEM. So today we have the next webinar in our show and tell series, and we're very pleased to welcome Chris Barnes from German Bioimaging, who will be speaking about OME-Zarr, a next generation file format for fair bioimaging data. So bioimaging data are becoming increasingly large and complex, and this brings new challenges for how we store, access, analyze, and share data. So today, Chris will be introducing OME-Zarr and NGFF, which are community-driven approaches to building open, interoperable standards for large-scale bioimaging data, with a focus on making data more findable, accessible, interoperable, and reusable. So Chris is a research software engineer at German Bioimaging, where he works directly on the OME-Zarr specification and contributes more broadly to the NGFF and Zarr ecosystems. Before this, he worked on tools and infrastructure for analyzing terabyte scale volume electron microscopy data for connectomics, including at the MRC Laboratory of Molecular Biology and the Genelia Research Campus. So we'll leave some time for questions at the end, so please add them to the Q&A tab as we go along, and I'll ask them at the end of the session. And just to note, this session is being recorded and will likely be shared on the CCP-volumeEM YouTube channel. So if there's anything that you'd like to catch up with from this session, then you should be able to rediscover it there. And with that, I'm delighted to hand over to Chris. Thanks again for joining us, and I hope you enjoy our session.
All right, thank you so much, Helen, and thank you to Helen and Martin for having me here. I'm really happy to talk to you all and talk to you about OME-Zarr. Um, I've got a little bit about me here, but Helen has pretty much covered it all. One of the things that I did at Genelia and in Cambridge was working on CatMade, a web-based viewer and analysis tool for image-derived connectomics data, as well as being the person who was in charge of storing our data and getting it into the physical servers, making it accessible to the researchers and things like that. So the concept of file format is very close to my heart. At the moment, I work with German Bioimaging. I've been with them since November in the research software engineer unit, contributing to NGFF directly, and also the specification and the tooling ecosystem around OME-Zarr. A lot of acronyms have been thrown at you so far. So NGFF, the next generation file format, refers to the goal and the process and the community driving towards a common data format for efficient access and sharing at scale. OME-Zarr is a specification which implements those decisions and hoping to meet those goals. OME-Zarr was originally called OME-NGFF, but it was later renamed to be more clear about what the actual format is. So a few of the tools around still do have NGFF in the title, so don't be too surprised if you see those around the place. So what's OME? OME, the Open Microscopy Environment, represents a community developing open standards and tools for interoperable image data since around 2005. You'll notice a theme here. Some OME tools that you might have come across include Omero, a web platform for cataloging and accessing bioimages. Bioformats, which you may be more familiar with, is a Java library which can read around 160 different life sciences image formats. That's used in Fiji, so even if you are not aware of having used bioformats, there's a good chance you have anyway. They also run the Image Data Resource, a public bioimage repository, and have previously developed OME-XML and OME-TIFF, which I would say are current generation formats for storing and exchanging microscopy data. The latter half is Zarr, which is a general data format for large n-dimensional array data. It's cloud native and it's self-describing. And this underpins the OME-Zarr format. And I'll come on to that in a little bit more detail later on. So some of the challenges which which mean that we need a next generation of file formats, is simply the scale. Increasingly, we are in the age of big data, and the problem with big data is that it is big. It means that we are also in a more disciplinary age, which means the ability to share data is even more important. It's not really possible to just post a USB stick with your experimental data or email a journal or anything else like that. We're talking gigabytes, terabytes, petabytes even for single data sets. Here's a slide borrowed from Matthew Hartley of a few public repositories of research data from nucleotide data to genomics, proteomics, some EM data with Empire and EMDB, and the Bioimage archive for general bioimaging. You can see that these image repositories are the ones growing fastest, and so yeah, the scale of data set that we're talking is just getting more and more problematic. Just to take it back to my connectomics roots, one example of a very large data set is this cubic millimeter of human brain that was imaged at 4 by 4 by 33 nanometer resolution. If we wanted to expand that approach to an entire human brain, just a single human brain, that would take about 2.5 zettabytes, which is that many bytes, which is about 1.5% of the whole internet volume by some estimates. To put it another way, if the first ever tetrapod birthed to a fish started watching Netflix in standard definition and today got an "Are you still watching?" break, that would be about how much data it had downloaded in that time. Once you add in backups, geo-replication, so you get faster access, any derived images like segmentations, we're really hitting up the boundaries of what might be possible to transfer data-wise. So there are lots of problems which come with scales of data. If the data is larger than your memory, maybe even larger than your hard drive, or even larger than what could be quite a large, beefy storage server, then you can't store it in a single file, which means you need to be scattering it across multiple files and coordinating like where the boundaries of those files are and so on. Corruption affecting even a small part of the data could throw off quite a lot of readers. So being able to validate each of those individual chunks is very important. And even some chunked file formats like HDF5 can't easily be written in parallel when they're in a single file. So really scattering multiple files across your file system is the way to go. The scale of the data also means that the data is more static because it's harder to transfer in its entirety between users. It's difficult for you to ship it from one place to another. But it's also more dynamic as we are increasingly multidisciplinary, as different labs are working on each other's data, and there's more of an emphasis on sharing data. The tools which are needed to deal with that are just more complicated and need more investment, which means that reinventing wheels is more and more costly and wasteful. So really having common data formats is absolutely vital. We already have many different file formats. I'm sure you may recognize some or all of these. This is obviously in itself a problem. As the data gets larger and larger, we can't just maintain copies in different formats to work with different tools. So it would be nice if we could converge on some community-driven shared format where one ecosystem with one set of tools can hopefully solve everyone. Of course, we have the problem of standard proliferation. It's not too complicated for every vendor and every organization to come up with its own solution to these problems. So that's why OME-Zarr and NGFF takes this community-driven approach. So we incorporate feedback from researchers, from vendors, and from developers in this quite tight feedback loop as we develop the tools and the specification alongside each other. So I'm going to go into a little bit more detail about Zarr itself, the vessel for OME-Zarr. and the specification for how to lay out the array data and the metadata on disk. If you think about writing a paper in a word processor, Zarr would be the .doc format, where OME-Zarr is the structure within the document. So abstract, introduction, results, methods, references, and so on. That's the sort of distinction to think about. Zarr splits large arrays of any dimensionality into separate files or objects on remote storage with some simple metadata. It's also worth noting a similar format which you may have come across, which is N5. Very similar goals, very similar format, which happened at pretty much the same time. But they are so similar that with a little bit of extension to Zarr, you can read N5 data. We settled on Zarr because there's a broader community around it, and there's a broader language support, and it's more flexible. So what does this chunking mean? Here's a simple 2D example of an array split into 4 chunks. The array and its metadata is then spread across 4 different files, the metadata in the zar.json file, and then 4 different chunks, which may then live in a containing group with its own metadata. If we only want to see that hashed blue area, we only need to read 2 of these chunks, which we can do concurrently because they're in different files. If we want to update a small region, we only need to rewrite a few chunks for the same reason, whereas if you were working in one big file, then it would be much more complicated to do that. And this tiling concept, just in 2D here, does extend into n dimensions, which is very useful for when you have X, Y, Z space, you have channels, you have time, and so on. Spreading those handful of files out into keys in some abstract store here sort of gives us the base understanding of how Zarr works to access these. And these files can then be stored on a file system locally, but they can also be stored on the web over HTTP, accessed over HTTP. Or they can be on any kind of object storage, so AWS S3, Google Cloud, Microsoft Azure blobs, and so on. Or if you're prototyping things locally, you can just stick them in a Python dictionary, or you can use an SQLite table or Redis or anything else like that. This is a really powerful abstraction concept for this storage, which allows you to plug in various other things like caches and failover stores and things like that, all within the same concept. So if you were to move your data from your kind of local test bed up to S3 for publication, then you would probably only need to change one line of your code, and the remainder should all work. So what does this metadata look like that we store alongside the arrays? This format, JSON, is trivial for computers to read and reasonable for humans as well. This kind of data makes up about 97% of web traffic. We have information about the array itself. You can see the shape and the data values and the data type here. The fill value allows us to just not even bother saving some chunks. So if you have a lot of black regions around the edges of your images, then you just don't have to save them at all, and then Zarr will interpret them as zeros. We have information about the chunking. So there are other chunk grids available, but this is the one that's most common, where we have for a 10 by 20 array, you have chunks of 5 by 5. And then there's some more information about how the chunk key encoding works, so that this C00, that is not necessarily the way you have to do it, but again, by default it is, and there's not a lot of reason to change it. The codecs are where things get more interesting. So here you can make decisions about things like endianness of numbers, which isn't too exciting. But you then also have compression, so you can compress data on a chunk basis, on a per chunk basis. And you can also do integrity checks. So if you've come across like Fletcher 32 or CRC 32C, checksums, making sure that no corruption has happened on a per chunk level. And even if you do get corruption on an individual chunk, then the rest of your chunks are safe. The last really important thing is this attributes key down at the bottom, where you can store any information you want. And this is what underpins OME-Zarr, because all OME-Zarr is a set of metadata that we add to a Zarr hierarchy. So Zarr has really good support across lots of different languages. Zarr Python is the reference implementation that's co-developed with the specification. Zarr's, the Rust implementation is also quite mature. There are bindings for that in Python, C, C++, MATLAB, Julia, and R. So you can get into Zarr data with whatever tooling you're using. So onto OME-Zarr itself. There are a number of different use cases that OME-Zarr supports, and those use cases continue to grow, which are, again, all based on community feedback. So at its simplest level, all we're talking about when we talk about OME-Zarr is a Zarr hierarchy which has some additional OME metadata in it here, which is all version. Yeah, it has a set version so that parsers can support multiple versions if they want. And all of this metadata is encoded in plain text. So even if you don't have direct access to the specific tooling, it's reasonably it's viable to have to look yourself about what is going on in there. So some of the features that OME-Zarr supports are naming your axes and giving the units and the type of axis that are involved. So at the moment, OME-Zarr is specialized for this up to 5-dimensional case. So two spatial dimensions, at a minimum, two spatial dimensions, and then optionally an additional space dimension, optionally a time, and optionally a channel dimension. But we're in the process of removing these constraints so that many more use cases can be supported. Another really common usage is to have multiple scale levels available for any given array. This is really useful for getting a broader overview at the top level of an array before drilling down into the really fine details. If you had to download the entire array just to get a broad look over it, you don't want that. So OME-Zarr gives us a layout for these multi-scales and descriptions of how coordinates in one space map to coordinates in another space. And just here's a nice little zoom. This is all happening in a web browser. Unfortunately, the video compression has made it look worse than it is, but I can point you to the link of where that data is later. So some features that are coming soon are the coordinate transformations. So we already have some coordinate transformations available, which are just for scaling and translations in between those scale levels. We are at the moment extending this. Sorry. We're at the moment extending this to cases where you have multiple arrays where you want to overlay them. For example, if you have images from different modalities, for correlative light and electron microscopy, for example, or if you have written some labels which are at a different resolution to the base resolution level of your original image. These coordinate transformations are also being incorporated into other projects, like spatial data, which works heavily with point annotations. If you can align your point annotations with images much more easily with these coordinate transformations, that's also very useful. Another thing that's coming down, another feature that's coming down the pipe is collections. So these are in a draft stage at the moment. And what this should allow is to allow references between different data sets. So a common use case is for one research group to publish an image, a raw set of images, and then for other researchers to add information to it, like segmentations and point annotations and so on. And so this collections feature will allow us to reference remote arrays from within one OME-Zarr dataset. All tied up with this is going to be an extensibility system. So rather than having to wait for the like fully robust development process to go through to get a feature into OME-Zarr, you'll be able to extend it for your own use case and build your own tooling around that. We are really excited for this to come in, but we also want to make sure that people are still like informing us of their use cases so that we can continue to develop OME-Zarr in a way which solves more and more people, so that we don't end up with those competing standards of half a dozen different labs doing things in slightly different ways. At the moment, we are at version 0.5, which has been pretty stable. We are coming up to releasing 0.6 pretty soon, and then we expect to be working on version 1.0, which is expected in Q1 2027. Based on and that's being funded by a significant grant from BioHub, formerly CZI. The goal is that there won't be any changes needed at the array data level. So if you've got your 10 terabyte volume, then going from OME-Zarr 0.5 to 0.6 to 1.0 will not require you to touch any of that array data, any of those chunks. It will just be some updating of the little JSON metadata file. So I would say that it is safe to start using OME-Zarr at the moment, because even if you later want to upgrade to a later version, then it will not take too much doing. And OME will be providing scripts which can update data from one version to another. So it's a simple, low-risk upgrade path. So obviously, as I said before, like it's not too difficult for any given organization to pile in and come up with their own solution to the problems that we've been talking about. So what's different about the NGFF process is that it is community driven. So we use this request for comments process, and it's all driven by community consensus. Where anybody can come in with a use case, with a set of user stories in particular. So as a microscopist, I want to be able to represent some particular situation. They can write up one of these RFCs, and then the community has an opportunity for feedback. And we have a loop of feedback and updating the RFC until it collects a number of endorsements. And in particular, endorsements from people who are implementing OME-Zarr. And this is really important because when you have specifications which are written primarily by people who are using one tool stack, for example, one programming language in particular, you tend to see design decisions creep in, which reflect that specific language or that specific tooling or use case. So having this community feedback and having lots of different people having an opportunity to write these implementations means that we can really iron out those and come up with a really robust final product. And then once the RFC has collected enough endorsements, then we move on to the specification phase, where the contents of the RFC get incorporated into the specification, implementations can be updated, and so on. It's also worth noting that adding to the OME-Zarr spec is not the only way to store the metadata that you need. As we saw earlier, you can really put any information you want into the Zarr attributes. So even if you have data which is not currently directly supported in OME-Zarr, you can always keep it in the Zarr attributes. And even though the regular OME-Zarr tools won't necessarily plug straight into it, then you don't lose that information. And your own tools can hook into it as much as you want. So on those tooling decisions, uh, we have really good support for OME-Zarr across lots of popular image viewers for bioimaging. So you may well have come across Napari, WebKnossos, Fiji in particular. Neuroglancer is quite a big one, and Omero itself, produced by OME. All of these can hook into the same data, and you should get pretty replicable results from viewing this data all together. And because all of the coordinate systems and the multi-scales and everything like that, there's a robust single way of reading these. On the software side of things, there's more than one implementation in Python because some of them have been quite exploratory. There are good implementations in JavaScript. The metadata has been implemented in Rust as well. And in Zarr Java, sorry, it's not OME-Zarr, it's Zarr Java, has an OME functionality inside it as well. So there's really good coverage in these common scientific languages. We can find out some more at the NGFF website, and I do recommend checking this out. This has all the specifications, including the one that we are working on currently, the 0.6 release. The RFCs which are coming down the pipe are also on this website, as well as a number of tools and tutorials, as well and an ambassador toolkit. So if you are interested in talking about OME-Zarr with anybody else, then we have about 100 slides already pre-selected for you. If you're more interested on the user side, I recommend going to the ImageSC forum. So this is more on the user side of things rather than the developers. And it's not just for OME, not just for NGFF, not just for Zarr. It's a really broad, really positive community for any kind of help with image analysis and image processing more generally. There are tags on there for OME-Zarr to make it easier to find the subjects which you might be interested in. If you're more interested on the development side and the software side, the Zulip that's associated with ImageSC is where most of those conversations happen. It's also really great to meet up with other people who are working on this kind of thing. And we've had some really good meetings already this year. There's a really thriving community around it. So the next one coming up is going to be in Zurich, which was a repeat of an event in the last couple of years, which has been great. Each time you can just get everybody in a room and make a lot of decisions a lot more easily. But then there are also more sort of auxiliary meetings that have happened. So spatial data, I mentioned earlier, hosted an NGFF-based hackathon earlier in the year. OME itself hosts hackathons. And of course, there was the VolumeEM has hosted a hackathon as well this year, which was a lot of fun to go to. So that's more or less the talk. I'd just like to thank everyone in German Bioimaging, Matthew Hartley at EBI. It was very useful. Some of the talks that he's given recently. Thank you to Helen and Martin for having me here, and the Zarr and the OME communities generally. This is from the OME meeting earlier in the year. So just one thing before we open questions, I would like to show some images that we have, some like example images. So there's this, hang on, there we go. So there are these SciViz data sets, which are just useful bits and pieces to prove that n-dimensional imaging works. And if we take the king snake, for example, then there's this tool, the NGFF validator, which allows you to read the metadata itself directly if you want a better idea of what that looks like in practice. And then gives you some information about the data itself. Um, and then also allows you to open it with various different web-based viewers or local viewers. And here is one in here is one. Sorry, the top of my screen is there we go. Um, so this is Neuroglancer, which you may have come across before. And this again allows us to scroll through with the chunks, make it really efficient to access smaller portions. And again, we can zoom in and out all the way and load new chunks quite efficiently. And with that, I think we can go to some questions if anybody has any.
Lovely. Thanks so much for that talk, Chris. That was such a clear introduction to the various challenges in this space and the different use cases as well. I have got my eyes on the Q&A box. So if any of our attendees would like to ask Chris a question about any aspect of his talk, please feel free to chip in there. Um, but in the meantime, while we're waiting for some questions to come in, I've got a couple of my own. So one of the things that I was particularly interested in because it seems really relevant to some of the work that we're doing on the CCP-volumeEM side was the process that you use to get comments from the community. I thought that that seemed like a really well thought through process to gather feedback about the different things that you're developing. And from my perspective, as someone that's quite involved in the core team of CCP-volumeEM, I was interested in some of the practical elements. I don't know if this is something that you know much about if you're involved on that side of things, but I was really interested in yeah, just the practicalities of how you do that. How do you get the comments? Is it something as simple as a Google Doc that everyone has access to that people can jump in on, or a GitHub repo that people can raise issues with? And I was curious about how you advertised it and the level of traction that you find that you get with your community in coming back to you.
Sure. Yeah. So you're exactly right. It is a GitHub repo, and so people can submit an RFC to just by raising a pull request to this repo. We do recommend that people reach out to some of the core developers earlier in the process, just to see whether it's sort of in scope for the whole project or if there's maybe a better home for it. Can save a bit of effort further down the line. Um, we then advertise when we get changes, when we get significant changes on that on ImageSC, that forum that I mentioned earlier, and the related Zulip as well. And these RFCs do get a lot of discussion at the meetings as well. So that is the main avenue that we have for advertising these changes. And then we get feedback through a few different channels. People can raise pull requests to write comments or endorsements directly on that same GitHub repo, which gives us really nice observability over like the timelines involved and who was involved and things like that. But if there are people who are like less engaged with GitHub and software development and things like that, we're also very happy to take an email and then we can shepherd their comments through the process. So we really get feedback from as broad a base of people as possible.
Mhm.
And then of the people who stay engaged, often RFCs become a bit of a pet project for an individual or a small group of people, which is really exactly how we want it. We don't really want to have a core group of people who are the only people making changes. and having spreading that responsibility and allowing people to drive the process themselves is really valuable, I think.
Yeah, yeah. I can imagine that it enables you as a team and the broader community to stay really focused on thinking about the usability of the changes that you're making sure that it's something that the community actually want when you have that distributed involvement where people feel that they can have a voice in the changes that are being made. Uh,
Yes,
people.
exactly. And the RFC process does mean that we are quite conservative about changes being made. But given that people are storing, terabytes of data and spending tens, hundreds of thousands of pounds to store their data, I don't think people want a file format that changes rapidly under their feet. So and because Zara is so flexible and allows you to store any of your own attributes and so on, it means that we can afford to be quite conservative and people can still store their information where they need it.
Yeah.
And the extensibility that we're hoping to bring in before 1.0 will add to that as well, where we can be conservative with the core and then allow people to define extensions in a more free way. This is a similar process to Zarr itself, where there's a long list of Zarr extensions which serve particular use cases, and people can specify themselves in a central location, and then implementations can choose whether or not to implement particular features.
Yeah, yeah, I think that that's a really interesting and important point about being quite conservative in the changes because like you say that means that you have a stable kind of concrete foundation which is so important when it comes to data because it's so upstream to everything else that is done but yet with the extensions and the flexibility within the file format it means that people can use this ecosystem in a flexible way to serve their own needs. So it's a really interesting example of having something that's kind of stable but also flexible.
Yes, exactly.
Yeah, yeah, and I think it feels that people would be reassured by that. I thought the point that you made in your talk about the simple low risk upgrade path kind of relates to that as well. And that
Yes.
feels very important when it comes, like you say, to data storage. When you're storing so much data, it's such an important part of the process that knowing, okay, well, this is going to be a stable ecosystem, there's a strong foundation, things aren't going to change too much. Scripts are being provided if things do change in order to
Yes.
support the movement between those systems. Yeah, it's really useful insight from the perspective of what we're doing on the CCP side. We have had a question come in on the Q&A tab that I will read. So it's from Chris Lewis, and he says, any plans for OME to make Amero useful for 3D OME-Zarr data? It currently is very good with 2D data, but has no great way to visualize 3D data.
Sure, yeah. So I can't comment on the Omero roadmap specifically because it's not what I work on directly. But definitely a tighter integration between Omero and OME-Zarr is what we want. And I think already Omero does incorporate some features to where previously Omero was mainly focused on data that was hosted on the same server as the Omero instance itself. It evolved more towards being able to point to remote data, which is very important for this bigger and bigger data that we're working with. There are already a number of web-based viewers for OME-Zarr data. So I can see it being quite tractable to incorporate one of those into the Omero platform. But again, I would need to ask Tom Bossonet if that is something that's specifically on the roadmap.
Great. I will keep my eyes on the Q&A just in case any of our audience want to chip in with any other questions or follow-up comments about that. So another question for me in the meantime. I was curious what your take was. It's quite a broad question. So what would you say are the biggest challenges within this research space at the moment? I wondered if they were related to the practicalities of software development, particularly software development within an academic context and the challenges that are associated with that, or is it challenges in adoption within the relevant communities, getting feedback from users, or something else? What are the most sort of challenging aspects of what you're doing?
Yeah, so I think you've hit a number of nails on the head, where for so we are lucky that we do have full-time engineers working on this, because yeah, exactly as I said earlier, there's the scale of the issues that we're dealing with no longer lend themselves to a PhD student who leaves the lab 2 years later and nobody can use their tools ever again. Um, so it's really good to have that sort of consistent backing, and because we are aiming to solve a lot of different problems with this file format. Certainly, Jerby has been able to has been quite lucky with getting grants and so on for quite stable support. Um, one of the issues that we face is that, as I said, the RFCs and specific progressions of the format tend to become sort of pet projects for some people. But often it's not going to be their full-time job, because we want researchers and the people using the data to be weighing in on it. But it also means that if it's only 5% of their time or so on, sometimes it can be a little bit slow to push these things over the line, just because a lot of the people involved have other responsibilities. And that's a cost that you pay for this kind of consensus model. Like if we were to go and run off and implement our own thing, then we could have it done quicker, but we wouldn't have that same kind of robust community following, I think.
Mm.
When it comes to people adopting the format, I think there are two main concerns. One of them is that nobody's microscopes are producing these things, are producing OME-Zarr off the bat. But there is interest in vendors from vendors in doing so. So often, if somebody takes their petabyte scale data set, then they probably don't want to immediately convert it into another format and duplicate all of their data before they even start processing it. So tying ourselves more closely with the vendors and saying, oh, look, these are the advantages of writing in this format directly, and these are all of the tools that you get access to. And that's quite valuable. And I think what's also very valuable is if the researchers buying this equipment can talk to the vendors and say, what is your plan for using open file formats? Because if people continue to invest in microscopes which produce closed file formats with very limited tooling ecosystems, then there's not a lot that the community can do to sort of get past those formats. And there are some formats in particular which are particularly complicated, or we are struggling a little bit with formats which are lossily compressed by default. So certain formats will JPEG compress anything that comes off the scope. And if you then want to convert your lossy images into a lossless format like OME-Zarr, you end up blowing up your data by 10 times. So people don't generally want to pay that cost, which is fair enough. And we are actually seeking to address that at the moment through Zarr codecs, which will work with lossy data as well. But that one is a little bit complicated as well. But it does come up regularly, and we're working on it.
Yeah, cool. I thought it was really interesting what you said just there about the challenges around the community involvement and having those pet projects. And I wondered, I can imagine that could be very challenging at points, particularly if there's a project that you see being developed and it's something that looks so exciting. And I wondered, are there cases where something has been abandoned and is still abandoned, not picked up, or do you have a process where you pull those projects back into the kind of core development team? Is there a formal process to handle those situations? Because I can imagine that people also probably feel quite a lot of ownership over their pet project, and it may have been abandoned, like you say, because someone has so many different commitments and roles and responsibilities. Yeah.
Yeah, absolutely. So there are definitely some RFCs which have been either deprioritized or which have ended up not being accepted. Sometimes over long distance and long time discussions, people don't quite get the same um, uh, you don't get the same like resolution power as you do with sitting in a room with people, which is why these community meetings are so important. Um, and so generally the RFCs which have been rejected are those which would have caused like uh, backwards incompatible changes. Um, so rather than break everybody's existing data for quite a minor gain in utility, sometimes we have to turn down something which we accept would be a good idea, but it's not worth yeah it's not worth scrapping terabytes, petabytes of data to do so. Um, in terms of sort of taking particular project under our wing, that's definitely something that has happened, and it's worth noting that the Derby RSE team that I'm part of has only existed since mid last year, and so there were some the coordinate transformations RFC, which we are working on at the moment and is close to completion, had gone a little bit fallow in that time. But now that we have the full-time engineers working on it, we've been able to make a lot more progress on it. And I think having us there also helps the people who originally brought up the issue that like they don't have to do everything themselves. And there are other people who are getting involved and working on it.
Yeah, yeah, and sometimes it takes that sort of critical mass or quorum of people that are interested to get the motivation
Yes.
project. And obviously the different specialisms involved as well, the complementary specialisms. We have had a couple of questions come in on the Q&A, so I will just read those. So the first one is from Anonymous, and they say, thanks for the nice talk. Which is the actual OME-Zarr status to support high content screening data, e.g. multi-well plates?
Sure. So there's actually very good support for HCS data specifically. I didn't go into it in my talk because I was thinking more about my own sort of connectomics volume EM background. But there is specific OME-Zarr data for plates and yeah for multi-well plates and then labels derived from those images and all of the multi-scale images works with the HCS specification and everything like that. So that's pretty well supported by a lot of the tools associated with OME-Zarr.
Great. And we've had a second question come in as well. That is, what was the first testing page slash link you showed just before Kingsnake?
Sure, yes. So this is the Insight Software Consortium. So this is a number of data sets which exist in other forms, which have just been converted into OME-Zarr for the purposes of test data. They're all pretty small, and they're all accessible on over Amazon S3. So should be easy enough to access remotely or download locally if you want. So hopefully that URL is enough for of what you're looking for. Another thing that is useful about these is we have this OZX format, which is basically that directory with all of the chunks and the metadata files stuck into a zip file. And it is just a standard zip file, which you can open with any zip tooling, but we make some recommendations on how to make it more efficient to access certain bits of it. But it means that if you look at this bag of files and say, "Oh, I don't really want to share my files by sharing these like lists of files. What if one goes missing?" Then we do have this OZX format. Again, this was raised by an RFC as well, um, and the open Sciviz datasets has OZX files for all of the datasets here as well. I think all of these are in version 0.5, which is the current version of OME-Zarr, and they were previously in 0.4, so I imagine they'll be updated to 0.6 when that comes out soon as well.
Great. We've had a couple of thank yous and a couple of people leaving, mentioning it on the Q&A. Um, great. So sort of a couple of questions to wind down. So
Sure.
moving forward, there might be attendees in our audience that have never interacted with this ecosystem before. Where would you recommend people start if they've been really inspired by your talk and this afternoon they just want to have a little bit of a play and think about how this world could be applied to their own data? What would be the first thing for someone to do?
So definitely the NGFF website, and if I can then in the resources sections, we have uh, learning and teaching resources, which include a number of tutorials. There are some Jupyter Notebooks, I think, in there. There's examples of using it with a Nextflow pipeline, which I imagine is already used by a number of you. Um, and that crosses a few different languages, using it graphically in Fiji or using it programmatically from Java or Python as well. As some recordings of talks, of past talks, if you want to dig a bit more into the history of the format. So that's absolutely where I would start.
Fabulous. And I would say as well, in relation to the CCP volume EM work that we've been doing, because you've mentioned quite a few different links and sources of information. So something that I will do in relation to this talk when I upload it to YouTube, I'll also create a placeholder on the CCP volume EM website from this talk to collate some of those materials that you've shared. So
Yes, and I will let you have the slides as well, so all the links will be accessible there.
yeah, I'll collate everything together so it's discoverable for our community and the people that are interested. And perhaps a related question, but maybe you'll have a different answer. Yeah, last question to wind up. If people only remember one thing from your talk today, what would you like that to be?
I would say um, big data is hard, but it doesn't have to be that hard. Um, yeah, and that investing in your infrastructure and in your community file format is the way that the future is going to go. Less siloing is better.
Yeah, it's well worth front loading some of that effort, isn't it? Yeah, fabulous. Well, that's a lovely quote that I can use in some of our comms around your talk. Great. Well, thank you very much to everyone that's joined us this afternoon, and thank you, Chris, so much for your talk and the time and energy and effort that you've put into putting that together and the work that you're doing as well.
Thanks again for having me.
Brilliant. And we will be hopefully having another talk next month, third Tuesday of the month as per usual. And the speaker is to be confirmed. And we'll be having a talk that relates to Nextflow, which you just mentioned, in July.
Great.
Yeah. And yeah, lovely. Thanks again, everyone, for coming and see you next month.